What is an empirical formula? Empirical formula is defined as the simplest ratio of elements in a formula. It's not necessarily the same as the molecular formula. For example, unrelated to this activity, if a molecular formula for, say, something like pimelic acid which is C7 H12O4. I got 16, I got to do some math in my head. It's organic molecule. 16 minus 2 is 14 minus 2 is 12. Good. And we got pimelic acid, yeah. And that actually is the empirical formula. Yes. You can't get a simplification. But how about succinic acid, which is C4H6O4. 8, 10 minus 4, good. Empirical equals. Can you simplify those ratios? There, you don't have to write any of this for activity. This guy got a break. Yeah. Don't have to write anything. So the simplest ratio in there is, well, they all divide by 2, do they not? Every one of those numbers, 4, 6, and 4. Do it. C, divide by 2, you get C2H. Wow. You get some interesting stuff is what you get. I don't even know where I am on the screen. There we go. C2H3O2. You can't simplify this one. You get fractions. You can't have fractions. Okay. So we need a strategy for these problems. They're not hard problems. If you have a strategy, it's really good. The best strategy is, since this is being done by weight, you know, percents are things out of 100, right? Your life is a lot easier if you say, I'm just going to assume there's 100 grams of this chemical in 100 grams of the compound. Here's the story. 49.31 grams are carbon. That's why 100 grams was a nice number, right? And now I got to figure out moles, because formulas aren't in grams, they're in moles, right? So we got 1 mole of carbon for every 12.01 grams. You're going to get me an answer. And I'll work on hydrogen here. 6.897 grams of H times 1 mole for every 1.008 grams. You're going to get me a thing. And then we're going to do 43.79 grams of O. 1 mole for every 16.00 grams. Forgot which periodic table I was using. On your periodic table, everything has been rounded to 4 significant figures. And I will get the answers after we pause. We're back. And we have our answers. In this molecule, there are this many moles of C, this many moles of H, and this many moles of O. But formulas don't have decimals in the formulas. We need to simplify these numbers so that we have integers. Your strategy. So far, our strategy started with us assuming 100 grams of stuff. That made these numbers instantly into grams. That was very nice. And then the next part of my strategy is pick the smallest of these three numbers and divide each of these numbers by that small number. So 2.736875 is the smallest number. Every single green number gets divided by that. And I'll save you some time. I know the answer to this last one. That's a 1. And divided by 2.736875. Yeah, I don't know what that one is. And 2.736875. I don't know what that is. But anybody got the second one? I'll pause. He was writing that number down a lot of times. Stop share. All right, we're back. And what we figured out was the ratio of these two was 1, exactly, 2.5, and 1.5. Now we have to make them all into integers. The last one is already an integer, but the top two are not. So when you end with a 0.5 right after the decimal, guess what number would be good to multiply to get rid of the 0.5? 2. While we're here are the most common endings on these numbers. When I say endings, it's like right after the decimal. If it was a 0.25 there instead of a 0.5, what would you multiply by? 4, because 0.25 is a quarter. If it was a 0.3333 here, what would you multiply by? 3. And the last one, 0.666666. Yeah, the last one. What was the 0.3333? You multiplied by 3. 0.6666 also multiplied by 3. That's right. It's 2/3 times 3 is going to be 6 over 3, which is 2. Yeah, it becomes a, yeah. So guys, you got to know your quarters are 0.25, your halves are 0.5, and your 1/3 is 0.33, and your 2/3 is 0.666. For both of those last ones, multiply by 3. For the quarters, you're multiplying by 4. For the halves, by 2. And that's as far as we're going to get in this class. And 141, you might be multiplying by 17 for some weird molecule. You never know. It's a trial and error thing. But you correctly said too, but you got to make sure you're doing it to every single one of these, right? You must do exactly the same thing to every number so the ratios stay the same, right? That makes sense? And this one's going to be, give me all the numbers because it's our first time doing this. And then I'll show you when you can decide you're finished with being an integer. So I know it's a little over 3, but I want everything. And I'll pause. All right, we're back. And here we go. When are we sure we have an integer? I know these are integers because I go to this decimal here. The second decimal, if the second decimal is less than 3, you are done. Otherwise, you're going to have to multiply by more stuff. Now, it could be a 0.99, right? Or a 0.98, or a 0.97. That's also within 0.03. If it goes what do we got? 99. Oh, wait. 0.98, 0.97, 4.99 round up to next decimal. Integer, not decimal. We're getting rid of decimal. So we're done. These are they're spot on. 3, 5, and 2. Final answer C3 H5 O2. Those were the closest integers to our things. So that is this molecule's empirical formula. And we're going to stop there.